Hello and welcome to this week's One World IMP Mathematical Physics seminar. For those of you who are our regulars, this is the series of IMP. For those of you who are new, you can find out more about our organization and the seminar series on our website. So the information is in the chat or under the YouTube video if you are watching it on YouTube. All our talks are being recorded and they are available on our YouTube channel. And if you want to know about upcoming seminars, then you can join our mailing list and find out about what's going on. And today, it's my great pleasure to welcome Sebastien Ott, who's going to talk about asymptotic expansions for spin ON models. So go ahead, the floor is yours.
Thank you. Thank you for the introduction and the possibility to speak to this seminar. And well, as was mentioned, I will discuss asymptotic expansion for spin ON model. And this is a joint work, or based on a joint work with Alessandro Giuliani, and it builds a lot on previous work by Bricmont, Fontaine, Lebowitz, Lieb, and Spencer back in the 80s, early 80s. And so I'll first introduce what is the main player, which is this spin ON models. And then I'll introduce what is the question I'm interested in and try to answer at least partially to that question. So first, the model is a probability measure on functions from ZD or the integer torus to the sphere. And the n will denote the dimension of the sphere, dimension +1. So this is the sphere in the n-dimensional real space. And we always suppose n is greater or equal to 2 to have a continuous spin model. And the model takes two parameters, the inverse temperature with beta, and a magnetic field H, which is taken positive. And it's given by the usual Hamiltonian that you can write and that is displayed on the screen with an interaction that favor local alignments of different points on the spheres, like neighboring spins will tend to align. And the magnetic field H breaks the direction, and I just fix it in the direction of the nth axis, but you could fix it elsewhere just by a global rotation of the model. So what are the properties of this model already in finite volume? Well, the model has a Hamiltonian, which is the interaction part is invariant at the global rotations and global ON symmetry, so that you apply the same symmetry to every spin in your model. So when H is 0, you have a global ON symmetry. And when H is positive, you have to preserve that the nth direction is preserved. So you still have some symmetry left, and you have a global ON-1 symmetry. You just broke one dimension by forcing the spins in direction n to be invariant, fixed by your rotation. So the model has a phase transition in dimension 3 and higher. And those will be the dimension I will consider for the whole talk, because a few things get simpler in this setup. If people have questions about dimension 2, I can discuss it at the end, but for this talk, I'll focus in dimension 3 and higher. And the model has a phase transition, meaning that it goes from a disordered state where everything decays exponentially, you have analyticity of everything that you want, and when beta is small, to a state where the model is globally aligned, meaning that it has a favorite direction, and you break the symmetry when the beta is large enough or temperature is small enough. And the questions I want to ask is related to the behavior of that model when the temperature is very small. So let me discuss what measures I want to consider, or like what quantities I want to study. So first, I want to study the model in the thermodynamic limit, and I want to study it without a magnetic field, but I want to study it in this phase where you have a spontaneously broken symmetry. So I want to take a thermodynamic limit, which is the first limit I take, with a fixed magnetic field. And then I want to decrease the magnetic field to 0 to be in the state with a positive magnetization in the direction n. And so this will be my setup. When I take those limits, I will assume something that is not entirely proven, but at least partially true, for what I want to do is that the measure you end up with, they will automatically be translation invariant because they start from measures on the torus. And so the finite volume measures are already translation invariant. And so the limits will also be translation invariant. And I will need some form of ergodicity. I will need that the magnetization field has a law of large, satisfies a law of large number. And this is, you can deduce it if you do those two limits when n equals 2 or 3 by using Liang theory. But when you have the higher spin dimension, you don't have Liang theory anymore. Well, at least it's not known whether you have Liang theory or not. And so you can't do the same argument. And you have to settle for suitable subsequential limits to have some form of ergodicity for the magnetization field. So this will be the measures that I will consider and that I will want to study. So what's the question now that I want to ask? Well, if I look at what is my model, what is the interaction in my model? Well, it's a point on a sphere. And if I am at my Hamiltonian that I had before, which is this scalar product, sum of scalar products, as the spins live on the sphere, the norm of one guy is 1. And so I can equivalently rewrite things as a sum of a square difference. This will give me the same measure. And if I look at what is the energy contribution for a pair of spins that are close to one another, if Si is very close to Sj, I can see it as almost a Gaussian interaction in the tangent plane to my model. So I have a sphere. The tangent space to that sphere is R to the n-1. And locally, my field of point on the sphere will look like a field with value in R to the n-1 and with an interaction that is quadratic in the distance between 2 points in Rn-1. So that's what is called a spin wave picture, that locally the Hamiltonian looks like the Hamiltonian of a Gaussian free field with one less dimension, so that the dimension of the spins of this Gaussian free field is n to the n-1. And that's the kind of thing I want to study. I want to see how close to a Gaussian free field with spin dimension n-1 is my model. And so one way, so that's what I said, is if beta is very large, you expect that the gradients get penalized if they get large. And so at small temperature, you expect to have something close locally to a Gaussian free field. One way to make sense of that is to say, okay, I can study correlation functions of my model. And I should be able to say, well, if I take some limit at t to 0, appropriate limit, I should see some Gaussian correlations. And if I look at what happens when t is positive, I should be able to say, well, if my model is really close to a Gaussian model, I can expand the correlation functions in series around t equals 0, the first coefficient being given by the formal Gaussian limit, and the higher corrections being given by seeing my model as a perturbation of a Gaussian. So let's make this a little bit more precise. For the XY model, which is the case in equals 2, how can you make sense of that picture? The first point is to rewrite things in coordinates that make this Gaussian structure a little bit clearer. And this is done, for example, by choosing coordinates that you parameterize the circle by an angle between -pi and pi. And if you rewrite your Hamiltonian, you end up with a sum of cosines between neighboring angles. And now the cosine, you can Taylor expand it. And this yields this sequence that I wrote on the slide. And if I can draw, you end up with don't need to draw, I wrote everything. You end up with something that is a Taylor series of powers of gradients of this field theta. So this is really the angle parameterizing my field, and I can think of this angle as being my coordinate in the tangent space of the circle. And if you look at what happens at the first line, I have a beta in front of everything. So what I can do is I can absorb this beta inside the angle by rescaling. And this, at least formally, gives me something that looks like a lot Gaussian free field. If you look at the last line. Yes. So if you look at what happens at the last line, the expression you get a constant term, which will be cancelled by the normalization. Then you get something that is the Gaussian field I was talking about previously, that you have this quadratic interaction. And this is precisely the energy of a Gaussian free field, plus something that is a perturbation. And due to my rescaling, what I have is that every term in my perturbation term has at least one t in front, or some power of t in front. And so I can see this, at least formally, as if now I plug in my interaction field t equals 0, I cancel this last part, and what remains is just a Gaussian interaction. So this gives me a formal way, at least, to see my model as a Gaussian free field plus a perturbation. And so that's what I wrote here. If you can rewrite your model. And one thing that I will do very regularly during the whole talk is that I will completely ignore the problem of the fact that even my rescaled field takes bounded values between minus square root beta pi and square root beta pi. And I will completely ignore that problem. This is not the main issue in what I want to say. And so I will just do as if this problem was not there. And so now what I wanted to do is to say, okay, I can write correlations of certain observables of my field as the Gaussian plus some correction and control the corrections. One way to do this is to say, okay, I have a Gaussian, I have a perturbation of a Gaussian, so I can formally do an expansion in power series in T of every terms that I have in every expression that I get, perform the Gaussian integral, and obtain something, some power series in T with some coefficients. And the first main problem that you encounter when you want to do this is that the series that you get is first not convergent, but already the coefficients that appear in front each powers of T will not be immediately well defined. So that because the Gaussian, the integration with respect to the Gaussian that you're making, you are integrating with respect to the Gaussian free field on ZD, and the covariances on this Gaussian field decay very slowly. And so if you do this formal integration of your formal expansion, you will get some terms that grow way too fast to be convergent. And so even defining coefficients in front of a formal power series in T is not direct. So this is the first problem one needs to cure. And the second problem is, of course, that, okay, if you have a formal power series, how close is it to really approximating your observable, or your expectation, or your magnetization, or whatever you want to compute? So what are the known results of this problem of saying, okay, I have a way to create a formal power series out of a model that is a perturbation of some Gaussian field? Can I make sense of this as a power series? And can I make sense of this as approximating my, my correlation function? And the first result that I want to mention is a result by Gavetzky and Kupiainen from the 80s, where they consider basically the model that I wrote here, but where you keep only the first power of T as a perturbation. So you have a grad phi 4 model, and they were able to perform this create Taylor series around T equals 0 for this model for the various correlation functions or for the free energy using a form of block spin renormalization. The second work, which is the one I will talk most about and on which we based our study with Alessandro, which is the paper by Bricmont, Fontaine, Lebowitz, Lieb, and Spencer from 81, which itself builds on methods that were developed by 4 amongst the 5 of these authors for the grad phi 4 model, the same as the previous one, where you perform these expansions by creating the expansion order by order using Gaussian integration by parts and controlling the truncation and all the error terms that could appear in your expansion using infrared bounds. And this will, I will discuss much more, so that will be the focus of the talk afterwards. Another body of work that I have to mention, but I don't know how many people really went into reading this deeply, is the work of Balaban, which spreads over 5 or 6 papers, where he develops a global multi-scale expansion for spin-ON models. And from this expansion that he obtains, which is a little bit in the same spirit as the block spin renormalization of the first paper, but technically much more involved, you can derive, amongst other things, the fact that you have asymptotic series in T for whatever observable you're interested in. So you can really develop in power series in the temperature any observable that you want around the 0 temperature limit. And the last work I want to mention is a paper by Garban and Sepulveda from 21, much more recent. And they go in a slightly different direction. And the model, all the models I mentioned have a perturbation. They have this Gaussian field plus perturbation, where the perturbation is a polynomial in T, in the perturbation parameter. And what they do is they consider a perturbation, the Villain model, where you can do the same kind of a Gaussian plus perturbation, but now the perturbation is not at a polynomial level in T, it's at a sub-polynomial level in T. So it has a much smaller effect on the correlations. And they were able to extract some corrections to the Gaussian free energy that you should obtain. They obtained the first correction term, non-trivial correction term, which is sub-polynomial. So now go into the main topic, which is how do you perform these expansions? What is the method that was developed by Bricmont, Fontaine, Lieb, Lebowitz, and Spencer? And I will present it again in dimension 3 and higher. Their method for the XY model was developed for the XY model and works also in dimension 1 and 2. For the spin-ON model, the generalization is slightly more complicated in dimension 1 and 2. So I'll discuss dimension 3 and higher. That's what we did with Alessandro. And what is on what is based their method? So I'll first explain it in the case of the XY model, and then I'll say what gets more complicated in the ON model and how can you fix the problem of what is getting more complicated in the ON model. So the starting point is the regularized version of Gaussian integration by part, which is the formula that I wrote here. So the first term on the left is okay, expectation of some correlation function under a Gaussian measure. And you can do the first term is the standard Gaussian, what gives a standard Gaussian integration by part, but where the covariances, or if you prefer if you imagine your field is the Gaussian free field, the covariants are replaced by the massive covariance. So you can get something that decays better than what you started with. But the price to pay is that now you have this last term, which is m squared times sum of blah, blah, blah. And this terms is the price for regularizing your propagator. So you got a little bit better decay in the covariances, but the price to pay is you pick up an additional error term. And so the game to generate the expansion will be to say, okay, I have a perturbation of a Gaussian. If I want to construct a Taylor series in T for one observable, I will generate it by performing successive integration by part. And I will use a regularized version so that everything that appears in my expansion converges nicely. And then I'll fine tune the mass so that I can neglect this error term that you get from the regularization. And I can remove the regularization for the terms that matter inside the covariances. So that's the spirit of their work. And how to control the error terms. Well, this is where infrared bound and so reflection positivity comes in. And the way you control the error terms is through reflection positivity, which gives you a control on the Laplace transform of linear functionals of your field. And so I rewrote a version of the Fröhlich-Simon-Spencer Gaussian domination, or infrared bound, as you prefer to call it. And one point that I want to mention here is to get the version I wrote here, where what you'll control is a linear observable of your field, the Laplace transform of a linear observable of your field. You can't directly apply what they did. What the method gives is that you can do the first thing that I wrote, but with the f function that sums up to 0. So you need some kind of the function that you're looking at, or the function you're taking the Laplace transforms of, is a gradient function, is a function of the gradient of your field and not of your field itself. And to reach the version I wrote here, you need to use some ergodicity of the measure mu beta h, or of the limit when h goes to 0 mu beta. So you need some kind of, you need a law of large number for magnetization, for the magnetization, or you need rather convergence in L1 of the average magnetization to the expected magnetization. And that's why I had to choose before the behavior of my infinite volume measure. I really had to say, okay, I need some ergodicity property of those, so I have to limit to take only suitable sublimits. So that's where the thing comes in. So how do you use this infrared bounds? Well, you use it to say this theorem that is basically saying, if you remember my spin model, I had a field in the direction n. So the coordinates 1 to n-1 of my sphere basically correspond to the coordinate that live in the transverse plane, so in the tangent space of my sphere. And so those ones should be my Gaussian field. And to obtain my Gaussian Hamiltonian, I did a scaling by square root beta. So if you look at what I wrote here, it's saying that I can control the moment generating function of my field square root beta times the transverse field. So you can see the first guy on the left as the Laplace transform of my wannabe Gaussian, of my field that should look like as a perturbation of a Gaussian. And this bound tells me that I can bound any moment of that rescaled field. And if you play a little bit with this, the field that I introduced in the case of xy that should play the role of the thing that is a perturbation of a Gaussian, this guy has moments of all order that are bounded uniformly in T. And this bound uniform in T tells me that when I will do expansions, I will be able to control everything just using the powers of T's that comes in front of expectation of certain correlation functions, and that I can bound the rest uniformly over T. And now let me do, I will do, in this case, I will do one simple computation to see how the method works rather than describing the whole method. And in the case of ON, I'll do the same and take a simple observable and do one step of this method to give you a bit of a flavor of what's going on. How do you control different terms? So let's say that the quantity you want to expand in powers of T is the energy of one edge, the expected energy of one edge. So what you first do is you say, okay, the field that looks like a Gaussian is not this angle field, it's this rescaled angle field. So the first thing I have to do is to make those fields appear. So I take my cosine, I expand in Taylor series, and I rescale the field by square root beta, which gives me all these powers of T's that I have now here. So I get these powers of T's by doing the rescaling, and I have my field, my wannabe Gaussian that appears in the equation. Now I can use the fact that the decay of these guys, the decay of the terms, the decay of these terms here, I control them by this infrared bound. These guys are bounded uniformly over T. And so everything that I need to know about how much they contribute to my expectation is entirely encoded by the power of T that is in front. So that allows me to truncate this series at a certain order. So that's the first type of use that we have from this infrared bound, which is it allows to say you can truncate Taylor's power series in T at a certain rate if you have because you have a certain control on the coefficient in front of the power of T. So once you did that, you end up with this sequence of coefficients where you have some expectation of a correlation of this phi field. And now you would like to say, well, what those mu beta of gradient square of my field gives me? And for this, that's where you start to do integration by part, is to generate a series for those guys in T. And so how do you do that? I have to remove these annotations. This. Okay, and so you do an integration by part by saying, okay, I want to compute the expectation of a function f. I can rewrite it as a ratio of Gaussian expectation, where now my Wt is my perturbation of a Gaussian. It was the thing that I obtained once I removed the Gaussian part of my field phi. And so I can do integration by part for the top guy, so for the guy f containing f e to the Wt. And I do integration by part, and then I reuse the rescaling to reobtain the starting measure. So if I do my integration by part, I end up with 3 types of term. So I do this regularized version. The first term that I obtain is this expectation, the purely Gaussian expectation. So this guy is some number that does not depend on my measure, spin-when measure anymore. The second type of term that I obtain is what happens when I do integration by part, the derivatives hit exponential Wt, and so it picks up the contribution from the perturbation to the Gaussian Hamiltonian. And the third term is the term that comes from having this regularized version of Gaussian integration by part, rather than doing the normal Gaussian integration by part. So basically the first term is the first order in my Tyler series. The second term will generate higher order terms, and the last term is a term I want to get rid of. So how do you now, the fact that you have a massive thing, all the covariances or all the Gaussian pieces that appear in these guys, they are all exponentially decaying, so everything is converging nicely. And so now I have, in a sense, to fine-tune the mass in order to be able to, from this expression, say something about Tyler series in T. So these two guys have sufficient decay because they are massive to give convergence. And the convergence is guaranteed because the Gaussian, the expectation with the spin-when measure is controlled because I have this uniform bounds on the moments via the infrared bound. And so now you have to do something about the first and the last term. So last term we want to remove, first term we want to say I can remove the mass, and this will be my nice Gaussian thing that I want to end up with. And the middle term, you have to study a little bit more the structure in order to say which part is relevant and which part is not. So you just study what happens when you differentiate with respect to the field, the phi field, this perturbation of the Gaussian free field. Do not worry too much about what I wrote. The important point is I started with a perturbation of my free field that was a gradient perturbation of the free field. And so in the end, what I end up with is I have the Gaussian covariances that appear in my expansion are covariance or two-point functions between gradients of the Gaussian field. So if you remember, I started with a expectation of a gradient correlation of my perturbation of Gaussian. And so doing integration by parts, I obtained something where the propagator is a point-to-gradient correlation. So I earned from the point-to-point, from just the Gaussian propagator, the fact that I compute the correlation on the expectation of a gradient observable, I earned a gradient. And so I earned a little bit of summability. And now as I hit a perturbation, which is a gradient perturbation, what I end up with is that the Gaussian covariance that appears in the expansion is a gradient to gradient. So I earned one more degree of summability. So I have something that decays better and better. And that's where the summability at the end will come from. And now I have I have some expression, and I want to choose M, and we'll see how to tune it so that you can say something by what we did so far. And so the first thing you need to control is we have this massive propagator that appears, and we wouldn't like to have this because we have something that is a perturbation of a non-massive Gaussian field. So we would like to remove the mass from the massive propagator. And then we have some sums of point-to-point propagator, point-to-gradient correlation, and gradient-to-gradient Gaussian correlation. And we need to be able to sum these and see how quickly they diverge when you take m to 0. We know that they diverge because the Gaussian free field has a too slow decay of correlation, but we want to control how fast they diverge when I remove this regularization parameter m. And you can see that the thing gets better and better as I have more and more gradients in my field. So the 2-point function decays like 1 over m squared, sum of the point to gradient like 1 over m, and the sum of gradient to gradient like log m. So now if we use those bounds in the thing that I had, so this is the expression I had. The first term, I just remove the mass. It's just one Gaussian expectation, so I can just remove the mass. This cost me m. Then I can remove this sum. I have an m square in front, and then I have something that is bounded, which is this mu beta correlation. There I have a uniform bounds on the moments, so this guy is uniformly bounded. And I multiplied it by some Gaussian covariance, point to gradient. And we saw that point to gradient, the sum of these decay like explode like 1 over m. So I have an m squared times 1 over m. So this is still nice and controlled. And then I have this big series in T, and I would like to truncate it to the order that I'm interested in and say that it doesn't hurt, and I can do it. And again, the mu beta part is uniformly bounded because I have uniform bounds on moments. And so I have only to worry about the summability of the Gaussian gradient to gradient covariance, which explodes like log m. So if I truncate at order n plus 1, so I keep only the n first powers of t's, the rest will give me a contribution that has at least a t to the n plus 1, and I pick up this divergence of the sum of gradient to gradient Gaussian, which gives me a log m. And so all of this is small if I take m to be small enough, like for example, something subpolynomial. So that's basically the strategy to do this expansion. I didn't tell you how to remove the m in the terms that we still have here but you can do basically the same thing as I did for the first term. It's more complicated, but you can still do it. And the idea is to generate this series. Now the first term that I obtained, it's just a constant, constant. It's a Gaussian expectation. It has nothing to do with the spin-one expectation anymore. And now in the terms that I have in my power series in T, I can carry on, and I can take this expectation of gradient to the 2k plus 1, and I can do again an integration by part to generate higher and higher ordered terms. And so I can generate the Tyler series by generating these terms, and I control the other term by choosing the mass appropriately. So this is basically the Bricmont, Fontaine, Lebowitz, Lieb, Spencer method for the XY model. And then, okay, what are the problems, or what did I use in this procedure? Well, at first I started with a correlation that is something that is a gradient observable in my quasi-Gaussian field, so my perturbation of a Gaussian field, to earn 1 degree of summability. And then I used the fact that my perturbation of a Gaussian was a gradient perturbation to gain a second level of summability. And so yet you can still get away with devil, and you can still perform expansions for non-gradient observables. And the way to do that is to say, okay, I still have other properties of my model. And these other properties is, for example, reflection positivity and infrared bounds. And from this, you can get some a priori bound on decay of correlation, on mixing, if you prefer. And you can say, okay, a non-gradient correlation, I can rewrite it as a gradient correlation where the two pieces in my gradient live very far apart. And so this almost factor out into a product of non-gradient correlation. And I can say, okay, then I can approximate the Tyler series for this non-gradient correlation by the correlation for my gradient, and I control how much they are close by using a mixing estimate. So that's basically what I wrote here. If you want the magnetization, you can instead study the 2-point function and use the fact that you have some bound on the decay of the truncated two-point function to say something on the magnetization from something on the two-point function. So now, okay, what's the picture when you take n larger than 2? So this was for xy, and we had a gradient perturbation of a Gaussian field, and we could do all this. So the first step I have to do is to give you some coordinates in which the spin-ON model looks like a perturbation of a Gaussian field. And this I will use just a generalization of the coordinates that we used for the xy, which are the generalized cylindrical coordinates, which is, you say, a point on the sphere, a uniform point on the sphere. I can sample it by sampling a uniform point on the n-2 dimensional ball and one angle in the transverse direction. So if I take the 2 sphere, I sample one uniform point between -1 and 1, and then I have to choose which angle I make on the circle of height of my uniform point. So this is one way to encode the coordinates. You can use other choices of coordinates, and you could probably still run the same kind of arguments. A very important point is whatever the coordinates you choose, you will never be a gradient perturbation of a Gaussian free field with spin dimension n-1. You will always have some term in the perturbation that are not gradient terms. And this is due to the positive curvature of the sphere. So you really have this problem that appears that is not present when you take xy. That is the complication compared to the previous scheme. And the way this will appear in the integration by part scheme is when you do integration by part, you will have correlations that appear that are not gradient correlation for the spin-ON field or for your perturbation of a Gaussian field. And so you have to incorporate in your scheme of integration by part, you have to be able to handle at this level, so a priori and not a fortiori, the fact that you can expand non-gradient correlation. So you lost 1 degree of summability compared to what we did before. So that's what I will describe now. So now your candidates for the Gaussian, as asked before, you take this the U coordinates are basically, if you imagine your sphere, the U coordinate are living almost in the tangent space. And the sine theta coordinate is basically the angle theta, and it's living in the last tangent space coordinate, while the cosine is living in the height of the sphere. So it's telling you how high you are on the sphere, so how close you are to the magnetized point. And then so the Gaussian field is a rescaled version of those spins. So I rescale everything by square root beta. And as before, I can rewrite my Hamiltonian like so. And if you take, well, you have one term that depends only on this U part, and one term that depends on a mixture of the U and the thetas. And if you do a Taylor expansion of the 2 square roots, and you do a Taylor expansion of your cosine, and you multiply that by beta, you have one constant term. And the first term that has no powers of t, the only term that has no powers of t in front, it's again just a Gaussian free field Hamiltonian for phi, so for the rescaled angle field, plus perturbations. But now the perturbations are really not gradient in U, they are gradient in the phi, but they will have like products of ui square, uj square. So you will have something non-gradient in the U coordinates. So that's what I said, that the first order that you are non-trivial contributing to the Hamiltonian is the Gaussian free field again. And now how do you fix that problem of having to take into account in your setup of integration by part the fact that you have non-gradient correlation appearing? Well, the same way you fixed it in the first place, which is there they used a fortiori the decay that you obtain from reflection positivity and the infrared bound on the correlation in the spin-ON model. And you use this decay, you take it, and you will plug it in the integration by part procedure. And this will allow to handle also non-gradient observable within the integration by part procedure. So what are the bounds that you get? Well, they are basically you get a decay of 1 over distance for the beta times distance for the non-rescaled field. And well, this is not a decay for our almost Gaussian field, but let's not worry about this and suppose that we have a decay for our perturbation of Gaussian field phi that is like 1 over distance. 1 over distance uniform in beta. It's not exactly true, and that's why it gets a little bit tricky when you want to implement this to make a proof. But to get to get why it works, you can just imagine that the correlation in this phi field in the spin-when measure, so really not in the Gaussian, already have a decay that is 1 over distance. So how do you now do a new procedure? So again, I will try to expand my favorite correlation, which is say, magnetization, and I'll try to expand it to first order already, just to see how I will use different ingredients. So this decay ingredient, and the second thing that we'll have to deal with is that we'll have many U correlation appearing, so expectation of correlation functions involving this U tilde field that I introduced. That is not a correlation function involving the phi field, which was the Gaussian candidate. And so we will need a way to say, okay, I can always rewrite things in terms of Gaussian at some point. So let's do that for the magnetization. First step, exactly the same way as for the XY, you expand in Taylor series, you use the fact that you have uniform bounds on the moments of rescaled field to neglect the higher powers. And so you end up with something that, a correlation that involves the U tilde field, a correlation that involves the phi field, and a priori some correlation that involves a mixture of the two. Then here I did one step of rewriting that the U tilde field, as I still have an ON-1 symmetry for my model, the different coordinates of the U tilde field all have the same law. And so I can rewrite this square as n-2 times the first coordinate of the U field. So basically the U field is invariant under an ON-2 action. And now how do I deal with the fact that I have a U tilde and not a perturbation of Gaussian? Well, I will use again this ON-1 leftover symmetry to recast this as a Gaussian or Gaussian perturbation of Gaussian correlation. And I'll do it by saying, okay, by definition of my coordinate, this U tilde direction 1 is the same thing as my original spin, so my guy on the sphere, rescaled by square root beta. Then this guy, well, it has the same law as the n-1 coordinate because it's invariant under an action of ON-1, so isometries isometries, rotation and reflection that preserves the nth coordinate of my sphere. So I can map it to something that depends now on S0 coordinate n-1. But now this guy, if I rewrite it with my theta and U coordinates, I get something that has some theta in it again. And I can redo the same game of I-Tyler expand what I obtained. And I keep the relevant terms. And as I looked at the rescaled field, what I end up with is that the first order contribution is the same phi 0. That's the leading order. And the higher order terms will all pick up at least 1 power of t. So basically what I can do is, when I have U coordinates, I can use the leftover n-1 symmetry to say I can convert those guys into something that at first order is the theta field, plus some correction that come with higher powers of t's. So they are saying, okay, at this level of precision, if I fix my level, the contribution is the same as the theta field. And if I want to look at higher precision, I have to get mixed correlation, and this mixed correlation come with a higher power of t. So if I fix my truncation order, this tells me how I should stop my my expansion and how much I should convert back this U tilde in a phi field. So this tells you what happens, what I should do with my theta field when I don't have any phi field left. And so the last thing I have to tell you is how to handle the fact that when you have a purely phi expectation, how do I get from this something Gaussian? And again, I will do Gaussian integration by part. I wrote a general formula, but you can see the same terms appearing. The first term is the purely the Gaussian term. The second term is the error term coming from the regularization. And the third term is the thing that comes from hitting the perturbation to the Gaussian. So now if we look at the different decays that are involved, well, let's do it in the case of the magnetization. The first term is a purely Gaussian term. The second term is the regularization, but now I don't have a point to gradient for my 2-point function. I told you before that what allows me to still say that this is small is that I have an m square in front, and if I had a point to gradient, I had a 1/m divergence. But there I don't have it. I have only a point to point, so I have something that diverges like 1/m square, so this is bad. To improve this, you can say, well, I have a 2-point function for the phi field under the spin-Wen measure. This guy has some decay. I can plug in that decay, and this boosts my bound to something better than 1/m square. And so I have something that blows up slowlier than 1/m square, and this will get me to be able to remove that guy and say that this will not matter in the expansion. So this will be smaller than any power of t if I choose the mass one. So that's basically how you want to use the decay for this error term. And the next term, you do the same. As you started with something that is non-gradient, I have some propagator that is a point to gradient, so that has slower decay. But you can again boost it by extracting some decay of correlation in the terms that is within the spin-Wen model measure. And so you can use this a priori decay to boost what you had for the Gaussian propagator to say, okay, I still have some ability and it's better than what I had before because I have some additional decay coming from the Wen measure. So the general procedure that you do is you write everything in terms of those u tilde and phi coordinates. You keep the relevant terms. You integrate by part the phi contribution by doing regularized Gaussian integration by part. You remove the regularization term, the error term, and you control the fact that you can remove the mass and the truncation of power series using the uniform bounds on the moments and the a priori decay on the spin-Wen model. And then you use this remaining n-1 symmetry to say, okay, what I had as a u tilde correlation, I can convert them back to some phi correlation as soon as I don't have any phi to integrate. So as soon as I integrated out all the phi contributions, I'm left with u tilde's contributions. I do a change of variable and I get back some phi's contributions and I can carry on expanding by integrating by part. And you iterate that until the end.
Excuse me, could I ask you to go back to the previous slide?
This one?
Where you were controlling terms which were not gradient. This is a crucial point, right? And you were controlling terms. No, I didn't quite understand how you did that. Could you tell us that again?
Yes. So the easiest one is this one. So this is the regularization coming from the fact that we use the massive Gaussian rather than the purely Gaussian. And so if I didn't have, I just say that this mu beta of phi x phi 0 is bounded by constant. This I get something that is order 1 because the sum over x of the g0xm, this diverges like 1/m square. But now I can say that this mu beta of phi x phi 0, it's smaller than 1/distance, 1/x. And so I have something that decays much better than what I had before. And this 1/x decay that I earned for this will basically tell me that I can now the divergence of the sum of point-to-point, massive point-to-point times 1/distance. This does not diverge like 1/m square, but only like 1/m 1 plus epsilon. So I obtain something that decays much better, or that blows up much slowlier than what I had with just the uniform bound by saying I can use the decay of this 2-point function in the Owen model to boost the summability of the massive propagator. And the same will be done for the next term. Here it's a little bit more difficult to see where the correlation will come in, but you can imagine I have a phi 0 on one hand and something that is morally an odd polynomial in phi x and phi x plus e in the other term. And so I can imagine that what I'll end up with is a linear combination of 2-point functions of the type phi 0, phi x, which will also have a decay of 1 over x, 1 over distance, which will be used to boost the bound that I had, which was a 1 over m divergence for the expectation of the point to gradient Gaussian. And if I add this additional decay of 1 over distance, I will get something that instead of exploding like 1 over m will only explode like log m, or some power of log m. Was it clearer?
Thank you.
And so, well, yeah, basically the end result is, okay, you can do with this modification on the procedure, you can do the expansion of any your favorite correlation function for the Spinor model as a Taylor series in T. And a nice point of the procedure is that you have an explicit algorithm telling you what will be the nth order contribution to your Taylor series. You have an explicit way you can feed it into a computer and it will spit out an expression in terms of sum of Gaussian correlations for the nth coefficient in your Taylor series. And I thank you for your attention.
Thank you very much for this very nice talk. Are there any questions?
But perhaps one answer, sorry, Hal.
Oh, no, please go ahead. I will probably Chuck.
So just questions. The lattice does not play too much of a role, only the dimension.
Yeah, the dimension plays a very important role, and the lattice is used in the fact that you need this infrared bound. So you need reflection positivity.
Ah, yes, that's right. Yeah.
Well, you could say, okay, I can also say I could take a weaker. I can take only the first 3 papers of Balaban, and I get the same bounds on the moments, and then I can do the rest of the procedure. But I'm not entirely certain that this is a simplification rather than taking the 4th and the 5th paper of Balaban and doing the same.
But you could use perhaps correlation inequalities also to.
Well, not for n greater or equal to 3.
Sure, but
yes,
yeah.
for the xy, for example, you could use other ways to get the bound on the moments.
Yeah, thanks.
But you need some way to get those bounds in. And so far for all n, I know only 2, which is reflection positivity and Balaban. But I would be very happy to find another one.
Mm-hmm.
So did you think about 2 dimensions and how the magnetization depends upon the magnetic field as it becomes very small?
Well, yes, in dimension 2, there are 2 questions in a sense. For example, first you could ask, can you do the same kind of expansion if you limit yourself to gradients, to expectation of gradient of the Spinor field? And that, I believe the answer is yes. And the reason is you have basically 2 scenarios. Either Polyakov is right, either Polyakov is wrong. If Polyakov is wrong, well, then you have a massless phase and you have infinite correlation length. And so on length scale, that should allow you to say, I see something where the gradient, the spin moves of order n. This will be seen in a short range compared to the correlation length. And so on very, very large length scale, I'll see something that is Gaussian. So I should have the same kind of asymptotic Gaussian expansion. And if Balaban is, if Polyakov is correct, you have a massive field, but the correlation length should still diverge like exponential of beta. And the length scale gets so large that on any polynomial length scale, you will still see something Gaussian. And that's what you need to get these asymptotic expansions As
No, I
if you
meant
don't
for
ask
the
more than.
XY model, because
But then if you add the magnetic field.
Yeah, if you add a magnetic field, there will be a magnetization, of course, and you might ask about how it depends upon the magnetic field. As the magnetic field gets small, what the coefficient is, that kind of thing.
And yeah, but that okay, yeah. So for XY, you don't have the problem of having something coming from the zero magnetic field. So there, well, I think there the main issue is you have to take part of the magnetic field into the Gaussian propagator.
Yeah.
And you should not have to regularize. So you should not have to add a mass. But yeah, and for XY, can you, with h as the small, I would say if you take a simultaneous limit t to 0 and h to 0, you can have something. But I don't see how to fix the temperature and then take small h. Because the field that you're perturbing around is not the Gaussian free field anymore. It's really the spin-ON model, the XY model in dimension 2. And this guy, we understand way less the correlation structure thing. You are the one who understood best the correlation structure of the XY in dimension 2. But I don't know how to perturb around the XY model with a small h. But I'm guessing that if you take a joint limit h to 0 and t to 0, you can probably say something about the way the magnetization goes to 0.
Thank you.
Okay, and any further questions? How did you want to ask a question?
Yeah, but I guess Chuck has a question, don't you?
Oh,
Chuck
No,
is unmuted, so.
No, I don't have a question.
Oh, okay. Yeah, I have several questions, but I was very much interested in your answer to Tom's question about doing 2-dimension for n equals 3, for example. So you showed us a plan which works in either case, but does it really work? I mean, can you use this infrared bound to get this uniform bound for perturbation series and so on, even without precise knowledge about the low temperature phase?
I think the only thing that is lacking so far, well, the thing that would make everything easy, I think it's still possible to do those expansions without it. But the thing that would make it easy is if you have some a priori bound on a point to gradient correlation in the spin-ON model. So what I showed is that you can, from the infrared, you can deduce something about the point-to-point decay. But now if you take a point to gradient, this should decay. Even the Gaussian in dimension 2 decays for the point to gradient. And if you get anything quantitative on the point to gradient decay that does not depend on beta, so it's really a 1 over, say, distance to the power epsilon, then the same procedure works exactly the same way. But one needs to get this.
But it doesn't come from infrared bound or anything.
Well, at least not that I know of. You can get something. You can get a point to gradient, but the gradient have to be in the right direction, and so you can't get the real point to gradient. You can get something on the gradient to gradient if the gradients are in the same direction. So you can get some information, but you don't. It's so far I haven't get to the point where it's enough to directly say that okay, the same procedure works. So one has to replace something at some point if we want to use the same kind of argument.
Thank you. Actually, I had one more very naive question. So if you work on this ON models and you have one preferred direction, so there is of course ON minus 1 symmetry. So all these n minus 1 directions are equivalent, right? But in your proof, you choose special 2 directions, and so you're not using this symmetry, right? So
well, in a sense we're using the symmetry because at the end we have to convert this U tilde back into the phi.
Yeah.
But like one direction is preferred because it's the one
Yeah.
of the magnetization.
Yeah.
So this
That's
guy is
necessary.
highlighted.
Yeah. Mm.
But yeah, like it's just that you want to say, okay, I want to say my field, I choose coordinate where the Gaussian guy
Yeah.
is if I quench the other direction, this
Yes.
guy is a gradient perturbation of a Gaussian. And that's the reason why we choose these coordinates.
So
But
is it, do you think it's a technical reason, or is there any deeper physical reason that you want to do this?
for dimension 3 and higher, I don't think that there is, this is just purely a technical reason.
Okay, thank you.
Any more questions? If not, then let's thank Sebastien again.
Thank you.
Thank you.
Thank you.